Have you ever stopped to wonder what's really running our modern world? I mean, what's the silent language that keeps everything moving? It's not the code on your phone, and it's not on your laptop. Nope, it's something way more fundamental, hiding right out in the open. So today, let's pull back the curtain on this hidden world of industrial control.
Seriously, just think about it for a second. That crazy, perfectly timed dance of a car factory's robotic arms. The traffic grid of a huge city that somehow works. Or even just the massive network that brings clean water right to your tap. What's the one thing that's orchestrating all of that?
Well, the answer isn't some giant supercomputer tucked away in a secret lab. It's actually a super tough, kind of boring-looking workhorse. A special kind of computer that has been the absolute backbone of industrial automation for decades now.
And here it is. Meet the PLC, or Programmable Logic Controller. Now, unlike your computer at home, this thing is built like a tank. It's made to survive all the heat, the dust, the vibrations you'd find on a factory floor. And it only has one job. Take in information from sensors and switches, and then, based on a program, control things like motors, valves, and lights with unbelievable reliability.
So, okay, how in the world do you talk to one of these industrial brains? Well, you use a language that, honestly, at first glance, looks like it was drawn up by an electrician back in the 1950s. And believe it or not, that's not an accident at all. See this? On the left, that's an old-school relay schematic. It's literally a physical wiring diagram. And on the right, that's ladder logic. See the family resemblance? This was a genius move. Ladder logic was designed to look instantly familiar to the electricians who were used to the old relay systems. It made the switch over to PLCs so much easier.
The whole structure is pretty simple. Just imagine power flowing from that left rail over to the right. The horizontal lines, those are the rungs of the ladder, and that's where all the logic happens. The inputs are basically just switches that can be open or closed. If you can make a complete path across the rung by closing the right switches, you energize the output on the right, which then, turns on a motor or a light. It's simple, it's visual, and it is incredibly effective.
But, and this is a big but, hiding under this simple visual is the single most misunderstood concept in all of PLC programming. And getting this wrong isn't just a simple mistake. It can be, as one expert puts it, totally disastrous.
And here it is, the one thing that trips everybody up. PLC instructor Jim Pidle is really clear about this. You should never, ever use the terms normally open or normally closed when you're talking about the programming instructions inside the PLC. Those terms, they only belong to the physical hardware, the actual buttons and switches that are wired up to the PLC.
Okay, this is where we have to draw a hard line between the physical world and the world of logic inside the computer. A physical switch, whether it's normally open or normally closed, that's all about its default electrical path. But a PLC instruction, it's not a switch, it's a question. A make instruction just asks its input. Hey, do you see voltage? Do you see a logical 1? And a break instruction just asks the opposite. Hey, do you not see voltage? Is there a logical 0? The PLC doesn't care why the voltage is there, only if it is or isn't.
Let's just break it down even simpler. The make instruction, some people call it examine if closed, is super straightforward. It just looks at its input. If it sees voltage, a logical 1, it says, okay, that's true, and it lets the logic flow right through it. If it sees no voltage, a logical 0, it just says false and becomes a brick wall. That's all it does. It's just a simple gatekeeper for voltage.
And the break instruction, or examine if open, is just the total opposite. It's actually looking for the absence of voltage. If it sees a logical 0, no voltage, it says great, that's true, and it lets the logic flow. But if it does see voltage, a logical 1, it says nope, that's false, and blocks the path. So it's an instruction that's true when its input is false. This separation of hardware state from the software question is what gives PLCs all their amazing flexibility. And this flexibility, this is where the real magic happens. By just combining these simple questions, we can build some really sophisticated control systems. So let's see how these basic building blocks actually come together. We can create fundamental logic gates so easily. Let's say you need an AND condition, right? Where two things have to be true to make something happen. Easy, just put two instructions in a line in series on the rung. The power has to get through both of them to get to the end. What if you need an OR condition where either one of two things can make something happen? Just create a parallel branch. The power can take either path. And just like that, with these simple visual blocks, you can build really complex behavior.
So let's look at a classic motor circuit.
You press the start button. That makes a make instruction become true, and bam, the motor output turns on. But at the exact same time, another make instruction that's watching that motor output also becomes true. This creates a little OR branch that seals in the power. So now the motor stays on even after you let go of the start button. To stop it, you press the stop button, which is wired to a break instruction. When you press it, the instruction becomes false, the logical path is broken, and the whole thing shuts off. It's this elegant self-latching circuit, and it's all built from those basic rules we just talked about.
So, ladder logic is visual, it's intuitive for electricians, and it's really powerful. Case closed, right? Everybody should just use this. Well, not exactly. In the modern world of automation, there's actually a huge debate raging. This quote from a technician on Reddit, man, it just cuts right to the heart of the issue. He's talking about ST, or structured text, which is another PLC language that looks a lot more like traditional computer code. And for the people who are actually on the factory floor at 3 a.m. trying to fix a broken machine, the visual nature of ladder logic can be an absolute lifesaver.
You know, it really just comes down to using the right tool for the job. Ladder logic is just unbeatable for straightforward on-off logic and for troubleshooting visually, right there on the spot. You can literally see the power flowing and find where the problem is. But structured text? It is way better for complex math or handling big chunks of data or running loops, all things that would just become a tangled, unreadable mess in ladder.
So why the fierce loyalty to ladder logic, especially in the US? Well, it's a mix of a few things. It's got those historical roots in the old relay diagrams. It empowers maintenance staff who might be wizards with electrical systems but aren't necessarily coders. Plus, in the US, the market leader Alan Bradley has one of the best ladder logic editors out there, and that just creates this cycle. Honestly, there's even a bit of a cultural vibe to it. Ladder feels like a tool for the trades, while text-based code feels like it belongs in an office.
And so this is the real tension at the heart of modern automation today. As our machines get smarter and smarter with things like machine learning and complex data becoming standard, will this language, born from 1950s wiring diagrams, be able to keep up? Or will its greatest strength, its visual simplicity, end up becoming its greatest weakness? That's the big question that's shaping the future of the factory floor.